Hello everyone, welcome to my class. Today is our first day of Calculus 2, and in today's class I'd like to review the U-substitution technique for integrations. So let me start the class right away. The U-substitution technique, also known as the U-sub. This is a technique for integrating a composite functions. The composite function is defined as f composite g at x equals to f of g of x. First, quick remark: every differentiation rule has a corresponding integration rule. However, computing an integral is not as easy as computing the derivative. There are several techniques for integrations. However, in some cases, there are no rules that absolutely guarantee obtaining an indefinite integral of a function. In Calculus 1, we studied the most common and useful technique for integration called the U-substitution technique. The U-sub is a corresponding integration rule to the chain rule for differentiation. So sometimes it also called the reverse chain rule. Let me give you the U-sub formula. The U-sub formula is the integral of f of gx times g prime x equals to integral f of u du. On the left side, this integral is the given integrals to us, and we substitute u equals to gx, then find its differential. So means compute the implicit derivative both sides, so du equals to g prime x dx, and we substitute those informations on the given integral, then it reduces to the right side integrals. So the main purpose of the U-sub is converting the complicated integrals to a nicer integrals which is easily integrable. Quick example. Example 1, 2 and 3. So 1, integrate 2x times under the radical of x squared plus 1. So here we put u equals to x squared plus 1, then its derivative turns out to be 2x dx. Great, that's the idea. I'll do those examples later. Similarly, another example is integration of x times sine of x squared dx. If we don't have x, then we cannot integrate sine x squared. So with the x there, then we can use U-sub technique to integrate such integral. In this example, we put u equals to x squared, then its derivative turns out to be 2x dx. The constant we can always manipulate, we can always move in and out of the integral. In the third example, integrate ln x over x dx. Though it looks like in the quotient here, but it's actually the product of two functions here, so we can compare the given integrals to these integrals here and apply the U-sub. So here we put ln x, u equals to ln x, then its derivative turns out to be du equals to 1 over x dx, and we can easily convert this x integral to the u integrals. Great. So some quick side notes on U-sub technique. Let me scroll down. First, finding an appropriate substitution for u is a bit of an art. One idea is to choose u to be some complicated part of the integrand whose derivative also appears in the integral. For example, here's in the first example. So under the radical, which is x squared plus 1, this term looks complicated than the 2x dx, so we put u equals to x squared plus 1. The key is to recognize the integrand as a composite function and choose u to be the inner functions whose derivative then turns out to be the outer functions. So in the example, first again, this is a composition of two functions. The inner function is radical x squared plus 1, and the outer function is 2x. So the idea is put u equals to inner functions, then its derivative turns out to be the outer functions. We can easily manipulate the constant. The new integral turns out to be the simpler integral than the given integral. Lastly, we need to resubstitute the variables to return to the given variable x. Side note number 2, it's not unusual to guess wrong. If your first guess doesn't work, try another substitution. Most importantly, practice, practice, practice. The more you practice, the more you recognize the pattern of the integrals. Let me give you a useful integral formula. So integration of 1 over x squared dx is negative 1 over x plus c, where x is not equals to 0. Great. Now with those ideas, now let's try to solve some example. Let's evaluate the following integrals. First integral, evaluate the integral 2x times under the radical x squared plus 1. So here, let's begin the solution. Choose u equals to x squared plus 1. Then take the derivative. So du equals to 2x dx. One derivative becomes 0. And look on the integrals here. So this 2x dx is the remaining term on the integrals. Great. So our choice, u equals to x squared plus 1, is the correct choice for this example. So then we have du equals to 2x dx. Then let's rewrite the given integral in terms of new variable, which is u variable. Then integral sign as it is. I denote the integral by I, by the way. So integral sign, then under the radical of x squared plus 1 becomes radical u. 2x dx. 2x dx is simply du. Now look, this new integral is easily integrable. So in the next step, radical u is same as u to the power 1/2. Use the power rule of integrations. U to the power 1/2 plus 1 is 3/2. So u to the power 3/2, and then dividing by 3/2. But we know dividing is same as multiplying by its is reciprocal, so we flip it. So then 2/3 times u to the power 3/2, and at the end, let's resubstitute our variables. So u equals to x squared plus 1. Then our answer will be 2/3, constant as it is. U is x squared plus 1, outside power 3/2, plus c. C is a constant of integrations. Great. I hope this computation makes sense to you all. Now let's move on. Example 2. Evaluate the integral x times sine x squared dx. Begin the solution. Choose u equals to x squared. Find the derivatives both sides implicitly. So du equals to 2x dx. And on our integral, the remaining term is x times dx. So I need to divide by 2 on our expression here. So divide by 2 both sides. And this gives me x times dx equals to 1/2 du. And then rewrite the given integrals in terms of u. So I equals to sine x squared. X squared is u, so sine u x dx. X dx is 1/2 du. Pull 1/2 outside, du. Correct. Then the next step, 1/2 copy as it is. We know the integration of sine u is negative cosine u. And put u equals to x squared. So then our final answer is negative 1/2 cosine x squared plus c. C is a constant of integrations. Great. Now let's move on. Let's do another example. 3. Evaluate the integral natural log x over x dx. Begin the solution. Choose u equals to natural log of x. Then take the derivative both sides. Du equals to 1 over x dx. Then rewrite the given integral. So I equals to integral log x is simply u, and 1 over x dx is simply du. So integral of u with respect to u is u square over 2. Resubstitute the variables, so u equals to ln x, so 1/2 times natural log of x outside is square plus c. Great. Now let's move on. Let's do example 4. Integrate ln x over x times under the radical 1 plus natural log of x outside is square dx. Here the integrand function looks terrible, but it's actually not. So let's begin the solutions. Choose u equals to 1 plus natural log of x outside is square. Then take its derivative. So left side is du, right side is the derivative of 1 becomes 0. So I don't need to write the 0 there. Then using the chain rules, first use a power rule, so 2 times natural log of x, then times the chain rule, derivative of the inside function, which is ln x, so ln x derivative is 1 over x dx. Great. If you look the remaining term on our integral, so ln x over x times dx, ln x over x times dx turns out to be du over 2. Then in the next step, rewrite the given integral in terms of u, so I is given integral equals to, first let's take care of this radical term, so 1 over this radical u, and then ln x over x times dx turns out to be du over 2. I pull 1/2 outside. I hope this makes sense to you all. Great. So now let's move on. And in the next step, 1/2 constant as it is. Let's take the integral of 1 over radical u. First, pull the radical u to the numerator by switching the sign in the power. So this u power 1/2, pull to the numerator, it becomes u power negative 1/2. And then take the integral. So the integration of u to the power negative 1/2 is u to the power negative 1/2 plus 1. So that gives you u to the power plus 1/2, which is here, and dividing by 1/2. That is same as multiplying by 2. So that 2 is coming from there. Then 2 cancel. In the next step, let's resubstitute u equals to this variables. Then our final answer is 1 plus natural log of x outside is square, everything outside is square, power 1/2 plus constant of integration c. I hope you have an idea now with just the routine computations. In the U-Sub, we first pick the u, and then we take the derivatives. We rewrite the given integral in terms of u variables. So our new integral has to be all in u variables. Then we integrate, and finally we resubstitute the variables to get the x variables. So our answer should be in x variable. Awesome. Now let's move on. Example 5. Evaluate the integrals 1 over radical 1 minus x squared times sine inverse x dx. Wow. So let's begin the solution. So choose u equals to sine inverse x. So keep in mind that when you pick u value, then you take the derivative immediately, then the derivatives turn out to be the remaining term on the integrand. So what happened if you would pick u equals to radical 1 minus x squared, then its derivative is not sine inverse x, then there's a problem. Great. So we picked u equals to sine inverse x, take the derivative both sides, left side is du, right side is the derivative of sine inverse x is 1 over radical 1 minus x squared dx, which is here, right? 1 over sine inverse x, we put sine inverse x equal u, then 1 over radical 1 minus x squared dx is simply du. Then let's rewrite the integral. Then this given integral I equals to 1 over u times du. Then you can easily integrate 1 over u. Next step, the integration of 1 over u is natural log of the absolute value of u. Then resubstitute the variable. U is sine inverse x, so our final answer is ln sine inverse x plus c. C is constant integrations. Great. Now let's move on. So we have another shortcut ideas here, which says integration of functions to the power n times the function's derivatives turns out to be functions to the power n plus 1 over n plus 1 plus constant. C means constant of integrations. But if you do not memorize this formula, just do the routine computations. So for example, example 6, integrate radical x plus 1 power cubed over 2 times radical x dx. If we use this formula, it turns out to be here n is 3. So here the derivative of radical x plus 1 turns out to be 1 over 2 times radical x. So then I can apply this formula. So according to this formula, first functions power n plus 1. So radical x plus 1 to the power 3 plus 1 is 4. Dividing by 4 plus c. Or we can use the U-sub technique. It's the same. Solutions. Pick u equals to radical x plus 1. Take its derivative both sides. So du equals to 1 over 2 times radical x dx. Then rewrite the given integrals. So I equals to integrations. Radical x plus 1 is u. So u to the power cubed times. Then 1 over 2 times radical x dx. 1 over 2 times radical x dx is du. Yes, just put du there. Then we can easily integrate the u cubed. So integration of u cubed becomes u to the power 4 over 4. Substitute the variable. U is radical x plus 1. So 1/4 radical x plus 1 to the power 4 plus constant of integrations. So which is here. Great. Similarly, another quick formula here. If we have a fraction functions to integrate where numerator is the derivative of denominator, then the integral of that fractions turns out to be natural log of the denominator. For example, let's do example 7. Evaluate the integral. Now here is my variable is z, e to the z plus 1 over e to the z plus z. Oh, I forget dz here. There's a dz. Then with that formula, this is the rational functions, or in the fractions form, where numerator is the derivative of denominator, right? The derivative of denominator, e to the z is e to the z plus z is plus 1. Then it falls under this category. Then according to this formula, the integration of e to the z plus 1 over e to the z plus z becomes simply natural log of the denominator and plus c. Now let's verify this result. So let's pick u equals to e to the z plus z. Then take the derivative both sides implicitly. So left side is du, right side is exponential function doesn't change. So e to the z is itself plus derivative z is 1 times dz. Then rewrite the given integrals. So I equals to here e to the z plus 1 times dz, the type here. So dz should be there. So dz gives me simply du. And 1 over e to the z plus z is simply u. Then integration of 1 over u is ln of u. And resubstitute the variables. U is e to the z plus z. So the final answer is ln of e to the z plus z. And then outside plus c. But c is a constant of integrations. So this one and this one will be verified. Great. Let's move on. Another quick trick here means integration of the lowercase f is uppercase f. Then the integrations of the lowercase functions of mx plus b, m and b both are constant, turns out to be 1 over the m means coefficient of x of this integration functions capital F of mx plus b. Great. Again, you don't need to memorize this trick, but sometimes it's just handy, or sometimes it's a shortcut to compute the integrals. But our old friend is just use U substitution. Okay, so let's do example 8. Evaluate the integrals of cosine 2x plus 3. So here is the, if I'm going to use this trick, then little f is cosine, the uppercase F is its antiderivative, which is sine, and I'm dividing by m is the coefficient of 2, so the integration of cosine 2x plus 3 happens to be 1/2 sine 2x plus 3 plus c. Now let's verify this result. So choose u equals to 2x plus 3, take the derivative, du equals to 2 times dx, then divide both sides by 2, so dx equals to 1/2 du. Rewrite the given integrals. I equals to this cosine angle 2x plus 3 is simply u, and dx is 1/2 du. Pull 1/2 out, du. Then 1/2 is outside as it is. Integration of cosine u is positive sine u. Then resubstitute the variables. U equals to 2x plus 3. So the final step is 1/2 sine of 2x plus 3 plus c. Good. Similarly, let's move on. Evaluate the integral e to the 5x dx. So again, with this formula, it turns out to be 1/5 e to the 5x plus c. Now let's use our U-sub technique. Choose u equals to 5x, then take the derivative both sides, so du equals to 5 times dx. Then dx equals to divide both sides by 5, 1/5 du. Then rewrite the given integrals. I equals to 1/5 e to the u du. Then the next step, 1 over 5 as it is. And we know the integral of e to the u is with respect to u is itself, and resubstitute the variables. U is 5x, then plus c. Awesome. So far so good, right? Okay, now let's move on. Another formula here, d, integration of 1 over 1 plus x squared is simply tan inverse x. We know the derivative of tan inverse x is 1 over x squared, right? In general, if you replace 1 by the constant a squared, then it turns out to be the integration of 1 over a squared plus x squared, where a is constant, turns out to be 1 over a times tan inverse x over a plus c. Great. Let's do example 10. So evaluate integration of 1 over x squared plus 9 dx. In this formula, our a is 3. So then this simply becomes 1 over 3 tan inverse x over 3 plus c. Now let's verify this result. So rewrite x squared plus 9 equals to, pull the 9 out. So 1 plus x over 9 means x over 3 squared. So here I want 1 plus x squared, and I can apply this formula. Okay, that's why you pull 9 out. Then choose u equals to x over 3. Then take the derivative. So du equals to dx over 3 and multiply by 3. So 3 times du equals to dx. I hope it makes sense to you. We can manipulate the constant, otherwise we can move in and out of the integrals. Okay. And then the given integrals I equals to, let's see, so we have x squared plus 1 equals to this term, so I can pull the 1/9 out, and this term is this term, so 1 plus u squared, and dx is 3 times du, so 3 times du. Great. Then this 3 and 9 cancel, so 1/3 outside, and we know the integration of 1 over 1 plus u square with respect to du by this formula is simply tan inverse u. Then we resubstitute the variables. U is x over 3. Then our final step is 1/3 as it is. Then tan inverse x over 3 plus c. I hope this makes sense to you all. Great. So please just pause the video and try to work yourself and try to understand this correctly. Great. Now let's move on. Let's do another example 11. Evaluate the integral 1 over 9 plus 4x squared dx. It's the same technique that we did for example 10. So it turned out to be this answer here. So again, let's work out here. So we want 1 plus x squared. Okay, so that's why I pull 9 out. Then this becomes 1 over 1 plus 4x over 9 is same as 2x over 3 outside square. Then with this formula here, 1/9 as it is, then 1 over a here. So my a is, or I can apply this formula here. So then let's use this formula then. Then tan inverse x. Now my x in my formula here, my x is 2x over 3. Okay. So tan inverse x, and by the hidden chain rule, I need to divide by 2/3. Dividing by 2/3 is same as multiplying by 3/2. So I flip 3/2 there, down there. Then we simplify. This 3 cancel 9 3 times. Then 3 times 2 is 6. So 1/6 outside. Tan inverse 2x over 3 plus c. Awesome. Great. So now let's continue. Let's do example 12. Evaluate the integral x over radical x minus 2 dx. Great. So begin the solution. Put u equals to x minus 2. Then take the derivative both side. Then so left side is du equals to right side is dx, because -2 derivative becomes 0. Then rewrite the given integrals. So before that, let's rewrite x also here. Write x equals to u plus 2, so that I can replace this x in the denominator in terms of u. So keep in mind, our new integral has to be an integral in terms of a single variable u. Okay, I cannot integrate if I have u and x term mix max there. I hope this makes sense to you all. Then the given integrals I equals to x is u plus 2, so u plus 2 on my numerator, and my denominator is simply radical u du. So here our new integrals is not easily integral. Now I need to do something extra here. So now from here to here, let's distribute our denominator. So integration sign as it is, u over radical u is simply radical u, because u equals to radical u times radical u, and one radical u cancel to the radical u in the denominator, so I have only one radical u left in the numerator, plus 2 over radical u du. Now this can be easily integrable. So the next step, so let's integrate radical u. Radical u is same as u to the power 1/2. Then the integral of u power 1/2 is u to the power 1/2 plus 1, which is 3/2, right? So u power 3/2 dividing by 3/2. So the denominator, you flip it, 2/3. So that's why this 2/3 is there. 2/3 u power 3/2. And substitute the variable back again, so u equals to x minus 2. So I hope it makes sense to you all. The first terms, it turns out to be this one. And then plus second term, plus as it is. Now 2 there. And then let's integrate the integration of 1 over radical u. First, bring the radical u to the numerator, so it becomes u to the power negative 1/2. Then take the integration of u power negative 1/2. So the integral of u power negative 1/2 becomes u power negative 1/2 plus 1, means the power is 1/2 now, right? So u power 1/2, then divide by 1/2. Dividing by 1/2 is multiplying by 2, so flip 1/2, so it becomes 2 times u power 1/2. U is x minus 2 and plus c. I hope this computation makes sense to you all. Great. Let's do example 13. Evaluate integrations 1 plus x over 1 plus x square. So here is another trick. We can distribute the denominator, then rewrite the given integral equals to integral 1 over 1 plus x square plus integral x over 1 plus x square. Then the first one is easily integrable, that's a formula, simply tan inverse x. And for the second one, that's also the formula, that means the formula I gave you, the integral of function over functions, means the rational functions, and if the numerator is the derivative of denominator, then the integral of that rational function is simply log of the denominator. The same idea here. So first find the derivative of denominator. The derivative of 1 plus x square is 2x dx. So that means I need to multiply by 2, divide by 2. So divide by 2, pull outside, so 1/2. Then the integration of 2x over 1 plus x square becomes log of 1 plus x square. Then plus c. Plus c is constant integrations. If you do not remember that trick here, then you can use the U-sub. Put u equals to 1 plus x square. Then the derivative of 1 plus x square turns out to be 2x dx, which we can easily rewrite this integral in terms of u and integrate and resubstitute back the variables. It turns out the same terms here, what we have here. Great. Now similarly, let's do example 14. Evaluate the integrals sine radical x over radical x dx. So our choice for u is radical x. Then take the derivative both sides, so du equals to 1 over 2 radical x dx. Then here I have 1 over radical x dx, so from here let's divide, multiply both sides by 2. Then 1 over radical x dx turns out to be 2 du. Then rewrite the given integral, I equals to sine u, then 1 over radical x times dx is 2 du. So pull 2 out, du inside. Great. So in the next step, the 2 as it is, integration of sine u becomes negative cosine u. That's why the minus sign there. Then resubstitute the variables. This equals negative 2 times cosine radical x plus c. Great. I hope you have more or less a idea now how to use the U-sub technique. Now the last example for today's class, let's evaluate integration of e to the power radical x dx. So now I have only one choice here. Let's put u equals to radical x. Then square both sides. Then u square equals to simply x. Take the derivative. So 2u du equals to dx. Then rewrite the given integral in terms of u variables. So e to the power u, and then dx. Dx is 2 times u du. U du, I pull 2 outside. Great. Then this integral is not easier than this integrals, right? Now I cannot move forward because I don't have the technique how to integrate such types of integrals. Now here the integrand function is the product of two functions. One function is algebraic functions, another function is exponential functions. And for such integrals we have to use another technique. The name of that technique is integration by parts. I wrote IBP, so that falls under the another section which is in 7.1. We'll start in our next class. Great. So then I will finish this question in the next class using IBP formula. Great. So thank you.